thermocouple because of this behavior. Means we'll discuss along with it. We'll discuss the significance also. Now I want that you should try to concentrate on the diagram. This is a symbolic way of symbolic representation of the law 1. This is your law 1, you can see. So in this case, um, what is the meaning of this diagram? In this case, you see that this is one metal, this is another metal. They are joined together, and we this is um, forming a thermocouple. And junctions are maintained at temperature T1 and T2. And if your, because as I told you that although this wire has been shown small, but generally these wires are very long. So in this case, if your wire, your your thermocouple wires are at different temperature, means I'm not talking about the uh, junction temperature. Junction temperatures are maintained at same value, but the temperature at the different part, means away from the junction, are different. Similarly, you can see that another same thermocouple is shown with another set of wire means wire temperatures. So these wire temperatures does not affect the final outcome. You'll get same net EMF. So this is a huge advantage your thermocouple offers, because you we discussed in detail when we are talking about the RTD or any other resistive temperature sensor, that your lead resistance is basically a huge error, the cause of error. And this lead resistance varies also. It's not like that the lead resistance is constant. You can measure the lead resistance and then you can make the correction for that. uh, because when the temperature and environmental condition changes, mainly temperature changes, then the lead resistance changes also. So the error is not constant, error is dynamic. So this issue is not present in thermocouple, because your output, that is proportional to the junction temperature difference, will remain same, whatever is the intermediate temperatures, means the wire intermediate wire temperature. So this is what the first law says. If anybody is having any query, you can ask me. I tried to explain it, but if you are not able to understand, you can ask me. You feel free to ask me. Yes, please.
Sir, can you please
जी
explain it again?
जी बताइए.
Sir, because I joined at late, that's why.
थोड़ा सा तेज बोलो, सुना ही नहीं पड़ रहा बेटा मुझे.
सर, आप एक्सप्लेन कर सकते हैं एक बार और?
एक बार और एक्सप्लेन कर दें. देखो ये
Yes.
बहुत सिंपल है. your output your output EMF voltage depends only upon the junction temperature. If your junction temperature, whatever may be the intermediate temperature, so if your junction temperature remains same, your output will be same. Intermediate means your wires, the wires temperature in between, away from the junctions, whatever may be. If it is changing, it is some other, maintain at some other, because it is exposed to the environment. So it will not affect your net output. So it won't affect your temperature measurement. It won't introduce any error. So this is what this law says. That's what I had written. The thermal EMF of thermocouple with junctions at T1 and T2 is totally unaffected by temperature elsewhere in the circuit. It states that the lead wires connecting two junctions may be safely exposed to unknown or varying temperature environment without affecting the voltage produced and hence the measurement. So this is what is the significance of this law, that is explained here. In first two lines, law is explained, means the behavior, empirical behavior, experimental behavior. These four lines basically explaining the significance of it. जी बताइए, समझ में आया कि नहीं आया?
Yes, sir. Thank you.
Anybody else? Having any question? Now, next law, if we are introducing any, if we are introducing here, you can see that this is thermocouple, and thermocouple is made up of two metals A and B, and its junction is maintained at T1 and T2. Now what is done in this case here in this diagram, that a third homogeneous metal, a third metal wire is C, third metal wire C is inserted in one of the metals, metal A. So obviously there will be two more junctions between A and C. So the junction, this is new junction because of the insertion of the third metal. So this is junction between two new junctions, this and this. If these two junctions are maintained at same temperature, then this insertion won't affect the output. Your net EMF, the output will remain same, provided that your junctions, your junction temperature remains same. So this insertion of the third metal, third homogeneous metal will not affect the output unless until if you are changing the junction temperature, provided that the insertion, the new junction should be maintained at the same temperature. Only then this will be. So you try to understand, and if you are not able to understand, then let me know.
सर अगर जंक्शन मेटल चेंज हो जाए तो कोई इफेक्ट पड़ेगा?
हाँ, क्या कह रहे थे आप?
सर अगर जंक्शन मेटल चेंज हो जाए तो कोई इफेक्ट पड़ेगा?
जंक्शन मेटल क्या होता है?
सर जैसे T1 A और B से कनेक्ट है, दूसरे में भी A और B से कनेक्ट.
T1 is a junction temperature. T1 is not the junction metal. T1 is junction temperature. T2 is junction temperature. Another junction. Originally we are having two junctions. This whose temperature is T1 and T2. Okay. Now
Okay.
we are inserting another metal here in A wire, and this insertion will result into two more junctions, which is shown here. If these, and because whatever junction that is coming into the existence because of the insertion of third metal, if these junctions are maintained at same temperature, then your output will not be affected at all. This is what this law says. What is the significance of it? We'll discuss it. So it is clear or not?
Yes, sir.
Okay. Now you see what is the significance of this law that I try to explain here in this diagram. So you see, this is your sensing junction, your measurement junction, thermocouple, which is made up of metal A and metal B, and the metal. This is your metal B. This is your metal A, and this is again another junction between original thermocouple junctions between metal A and metal B. This is suppose reference junction. This is your measurement junction. This is reference junction. Now you see your copper wire you are inserting to connect a voltmeter so that you can measure the output. So here you see we are inserting a copper in one of the metals, and if these two junctions are additional junctions which is coming into the existence because of the insertion of copper in the circuit, if they are maintained at same temperature, then this insertion won't affect the output voltage. It only affect the output voltage. It only depends on the output voltage, only depends upon the junction temperatures. Yes, please. This is the significance of law number 2. If anybody is having any question regarding this law, you can ask, please. And this significance. जी, समझ में आ गया या यू आर नॉट एबल टू कॉम्प्रहेंड? जी भाई, हाँ नहीं तो बोलो,
हाँ जी सर।
आगे चलें।
यस सर।
Now this is next law. Here in this case, if a metal is inserted at one of the junctions, this is your original thermocouple, which is made up of metal A and metal B, and junctions are maintained at temperature T1 and T2. Now, if this, you can see that the metal C is inserted at one of the junctions, and here obviously one of the junction will form with A and C, another junction, new junction I'm talking about, because of the insertion of the metal. So two new junctions will come into the existence. One will be between A and C, another will be between B and C. Again, if these two new junctions, actually we are splitting the original junction into two junction because of the insertion of this new metal. So if these two junctions are maintained at the same temperature, that is T1, then again your output will remain same, your EMF will remain same. Now please let me know if you understood it or not. Obviously this new junctions are maintained at the same temperature as that of your original junction. So your junction temperature difference remains same, so output will remain same, and this insertion will won't affect. And another thing is that even if in this inserted metal away from the junction is having some other temperature, that is not also going to affect your output. It solely depends upon the temperature difference of the junction. Here also this is valid. Whatever is the temperature away from the junction, that is not going to affect your output. You will have same EMF. So let me know what is your take on this law. If you are not able to understand, let me know. जी
Sir,
बताइए
this law is also related to first law, na?
जी.
This law is also related to first law. That is, if we are
Just a
until
minute,
and
just a minute,
unless.
just a minute, just a minute, just a minute.
Yes, sir.
I'm asking one thing, whether you are able to understand this law or not.
Yes, sir. Understand.
It is related to first law as well as second law also. Here means you can correlate with any law. That is not a business right now. I'm just asking you are able to understand this particular law completely or not.
Yes, sir. Able to understand.
Okay, now the significance of this is this. You see, here we are having a thermocouple made up of chromel and aluminum, two different material wires. This is your sensing junction, and then you are inserting the copper here, third metal here. In chromel, one of the junction is with the chromel, another junction is with the alumel, and this junction is maintained at the reference. These junctions are maintained at the reference temperature, and they are maintained at a constant reference temperature, and then we are connecting it. So you can see that the resultant junctions are basically maintained at the reference temperature, so it won't affect the output. Whatever is the output because of the maintenance of the temperature difference, T measurement and T reference, it was without this copper wire inserted into it, or it will remain after same after insertion of it as per the law, because these two new junctions that came into existence because of the insertion of copper wire, one with the chromel and another with the alumel, it is maintained at the same temperature and at the reference temperature, so your output will remain same as per the law number 3. Is it okay to all of you? जी बताइए. ये समझ में आया कि नहीं आया?
Yes, sir.
This is the significance of this law. Now I'm coming to another next law. Here you can see that we are having two metals A and C. Here and the junctions are maintained at T1 and T2. Suppose the output voltage is EAC. Now we are having another means we are connecting another metal with the C, like C and B thermocouple is made, and then your junction temperature remains same T1 and T2, and your output is ECB. Now we are having the first metal and the last metal together, and the output will be sum of these two voltages, whatever output you are having. So this law is basically called law of intermediate metal. Law of intermediate metal. Here in this case, you see we are having one common metal in these two thermocouples. That is C. We are having AC and we are having CB. Now, if we are having output of these two for certain junction temperature, for certain, obviously your junction temperature remains same throughout. So for certain junction temperatures, so if we take the combination A and B without the intermediate metal, then it will be equal to sum of these two voltages. That is what is the law of thermo. What is its significance? I'll let you know. First of all, you should let me know whether you are able to understand this or not, whatever law I had explained just now. Yes, please. भाई समझ में आ गया तो हाँ बोलिए, नहीं समझ में आया
Yes,
तो
sir. समझ में आ गया, sir.
समझ में आ गया आपके. Now what is the use of it? Actually, I had shown you the calibration table. So what is done, the all possible metals, whatever metals which can be used, which are having attributes to be used as a thermocouple material, they are basically calibrated with respect to common metal C, and generally this metal is platinum. So now you are having all the metals calibration table with respect to one common metal. Generally platinum is used. Then if you require any combination, AB, AD, AG, AH, whatever combination, or BD, any combination, so then you are not required to perform the experiment again and get the. So if you are having the table, calibration table for AC and for BC, then you just add them, you will get for AB. Or by the matter of fact, with any metal DC, any metal EC, whatever. So this way, because you see calibration tables are experimentally very means you can say accurately, you are supposed to accurately in the sense that whatever is the technology, whatever the standards you are having, you should use the best of the best technology and best of the best standard to find out the calibration table for any thermocouple. So this, to have a general and because platinum is a stable material also, so all the metals, possible metals, are combined with the platinum, and then calibration table is measured. Then for any other combination we can add it. You can see that by adding those two tables, we can find out the calibration table for any combination. So are you able to understand significance? That's what I had written. All possible combination of metal need not be calibrated, since individual metals can each be paired with one standard metal, generally platinum, and calibrated. Any other combination then can be calculated. Is it fine to all of you?
Yes, sir.
Now I'm coming to the final law. Here you can see that we are having metal A and B, and junction temperature T1 and T2. Then we are having again metal A and B, and junction temperatures are T2 and T3. Here it is T1 and T2, here T2 and T3. So one of the junction temperature is common. So output is E1 and output is E2. Now if we maintain the thermocouple at T1 and T3, then output will be equal to E1 plus E2. This is what is the law number, last law, empirical law. Is it fine to all of you?
Yes, sir.
Now its significance is very important. As I told you that all the calibration tables, in all the calibration tables, I'm talking about the standard calibration tables, the reference junction temperature is kept at 0 degrees Celsius. So we always want that our reference junction, while measuring the temperature, we want that our reference junction temperature should be maintained at 0 degrees Celsius. But this is not always possible. If you are making a measurement not in the laboratory, so in the field, then it is not possible that always carry a ice bath with all temperature maintenance mechanism. That is not possible. So obviously, the another condition is basically satisfied that we keep whatever is the temperature other than 0, we try to keep it at constant value. So in that case, you cannot use the calibration table directly. I'm giving you one example. Suppose your junction temperature here, it is 80 degrees Celsius, and it is 0 degrees Celsius. Then you will get certain voltage. Now because this is your measurement, it is basically at 0 degree at 80 degrees, remain at 80 degrees Celsius, but this is at the room temperatures, suppose 25 degrees Celsius. So your measurement temperature remains same. Your output voltage at the higher reference junction temperature will reduce. Now if you are reading this value directly from the table, then the temperature will be less than 80 degrees Celsius because of this higher reference junction temperature. So this is a potential cause of error in measurement of temperature using thermocouple, when your reference junction is not maintained at 0 degrees Celsius. And this is a pertinent issue. So we require certain compensation so that we can find out so in this case, we are required to add and subtract the additional voltage to it so that you can reach to the so we want this voltage, whatever voltage we are getting, but we want this voltage to be equal to only then to be equal to the voltage when this thermocouple will produce when the reference junction is at 0 degrees Celsius for any sensing temperature. So when this will occur, only then you can use the calibration table. So how this is done, whatever process that is adopted to do this is called reference junction compensation. It is called reference junction compensation, and this rule is used for this purpose. This particular, the last law is used for the reference junction compensation. Now I'm coming to how this is used. Significance of law 5, reference junction compensation. So you see, this is a thermocouple which is at that for a specific for a specific junction temperatures like T1 and T2, you are getting E1 as an output voltage. Now I'll try to explain you. Suppose T2 is more than 0 degrees Celsius. T2 is more than 0 degrees Celsius. So obviously E1 is directly proportional to T1 minus T2. Now if we are going to suppose it is 2 point some millivolt, like, and we are using this suppose it is 2.737 millivolt. So your junction, your measurement junction, if we are not making any compensation and using table as it is, so your measurement junction temperature will be or unknown temperature will be 151 degree Fahrenheit. Okay, so this is not correct temperature, because here in this table the reference junction is maintained at 0 degree Celsius, whereas here in this case your reference junction is not maintained at 0 degree Celsius, but it is maintained at some other time. So what to do? So obviously whatever temperature that we read from the table, this temperature, unknown temperature, is more than that, because this temperature difference is less in that for same junction temperature, because T2 is more than 0 degree Celsius, so E1 is less. If T2 is 0, then obviously E1 will be more for the same junction temperature, because your difference will increase, will get enhanced. So this is the problem that we face when your reference junction is not maintained at 0 degrees Celsius. Then we go for the reference junction temperature. As I told you earlier also, that when we are measuring the thermocouple, so the essential condition is that your reference junction temperature should be maintained at constant value, and it is most desirable if it is maintained at 0 degrees Celsius. But if it is not maintained at 0 degrees Celsius, then it should be maintained at constant value, and whatever is the value of the reference junction, value of the temperature at which your reference junction is maintained, it should be accurately known, whether it is a 0 degree Celsius or more than 0 degree Celsius or less, whatever. So it should be known. So you know T2. Now what will we do? We will go to the table of the same thermocouple, and we'll try to find out the thermocouple output when one of the junction of the thermocouple is maintained at T2 temperature, which is already known, and another at 0 degrees Celsius. Is it fine to all of you? So we'll note it down. We will note it down. That is, E2 is directly proportional to T2 minus 0. This value we will get from the table. Is it fine to all of you? So we have noted down E1. We have noted down E2. That is for the same thermocouples. For the same thermocouple, when your one of the junctions is maintained at T2 and another junction at 0 degrees Celsius, because we are reading from the table. So obviously in the table your reference junction is at 0 degrees Celsius, and your another junction is maintained at T2. That is basically the reference junction temperature of our original thermocouple setup. Now, as per this law, your intermediate temperature is T2, you can see. So obviously if we are taking temperature T1 and 0 here, so it will be equal to E1 plus E2. So this is basically compensated, you can see that. Now this is the situation where we can use the table directly. This is the situation. So here you can see that E1 is directly proportional to T1 minus T2, E2 is directly proportional to T2 minus 0, E1 plus E2 is directly proportional to T1 minus T2 plus T1 minus T0, and T2 will get cancelled. So E1 plus E2 is proportional to T1 minus 0. Now T1 we are interested in finding out. T1 is unknown temperature, and this is the situation under which we can read the table directly without any. So compensation is done. So here we can for the same measurement junction, we are able to find the voltage when reference junction is maintained at 0, and now this voltage can be used to read the table to get the accurate value of the unknown temperature. This is how the reference junction compensation is done, and this reference junction compensation is required only in the case when you are not able to maintain your reference junction at 0 degrees Celsius. It is at some other temperature, then you can use. So this is a very important thing. It is asked in many interviews. So if you are having any query about reference junction compensation, please let me know. अगर कोई चीज आपको समझ में नहीं आई हो, पूछ लीजिए आप. जी
सर, जब हम टेम्परेचर को 0 डिग्री, रेफरेंस टेम्परेचर को 0 डिग्री पे मेंटेन नहीं कर पाते, तो सेकंड केस में हम जब 0 डिग्री पे रेफरेंस को मेंटेन कर पाते, तो T2 को भी हमको मेंटेन करना पड़ेगा सेम.
ये जो स्टेप है, ये हम टेबल से आपने ये थर्मोकपल लगा दिया है ना, तो इसमें हमको T1 मालूम करना है ना. तो T1 हमको नहीं मालूम है, T2 हमको मालूम है और E1 मालूम है. बात समझ में आ रही है?
यस सर.
तो ये T2 टेम्परेचर क्या करेंगे हम, ये फिर मेंटेन नहीं करेंगे थर्मोकपल को, हम टेबल से पढ़ लेंगे.
ओके सर.
है ना, टेबल से पढ़ लेंगे.
Yes,
तो हमें E2 मालूम हो जाएगा और ये E2 इसमें E1 में जोड़ देंगे. ठीक है.
यस सर.
और उसके करस्पॉन्डिंग हम टेबल से टेम्परेचर पढ़ लेंगे. एक्सपेरिमेंटली ये करना है, लेकिन एक्सप्लेनेशन ये है, लॉ यूज किया हमने ये लास्ट वाला. ठीक है.
यस सर.
सबको समझ में आ गया? Okay, so this is about the empirical laws and their significance. Now I'm closing this topic here. If anybody is having any question regarding thermocouple, this is the last chance. You can ask anything from starting to end. If you are having any question regarding thermocouple, you can ask this. Okay. Now I'll discuss another topic. Now we'll discuss the capacitive and inductive sensors. So we started with the resistive sensors. We discussed strain gauge, RTD and thermistor. Then we discussed the active sensor thermocouple. Now I'm going to discuss the capacitive and inductive sensors. Although I'll discuss capacitive sensor as a level liquid level measurement. So I'm starting with the liquid level measurement. So first of all I'm discussing some primitive techniques, and then I'll discuss some other. Then I'll discuss the with the help of I'll discuss the capacitive technique for the liquid level measurement. Now this diagram is self-explanatory. Here you can see that here you can see that liquid level of the tank we are interested in finding out, and then there is extension of this tank. YouTube is connected to it, which is full of mercury, which is filled with the mercury, and then we are having a resistances, discrete resistance values are here. So as the liquid level increase, obviously this mercury will increase, level will increase in this tube. So more and more resistances which are connected in parallel, they will get means they will connected in the circuit in parallel, and obviously your current, your resistance will decrease as the more and more resistance are coming in parallel. So your resistance will decrease. So for same input your current will increase. So as that liquid level increase, your current will increase, and then you can calibrate this current in terms of the liquid level. So this is how resistive method is used. Although this is not a very good method, it's not considered as a very good method. but because your certain kind of insertion is there. But this is a method for the sake of completion. I'm taking it. It may be used earlier, but it is not a very common method nowadays. Um, so this is about the description about that. Then float method. That is float method is although it is also a simple and primitive method, but this is at the domestic level, and some industry also it is used even till today. So there is a float. So as the float will because at the liquid level will increase, the float will also rise, but because it floats on the surface of the liquid, and then your output is connected to the, the variable terminal of your potentiometer. This is your potentiometer. So as the as the float moves up and down, accordingly your moving terminal, the variable terminal um, uh, of the potentiometer will also vary up and down, and accordingly your voltage will vary. This voltage will vary. So you can see that with the help of float, this mechanical, you can say, sensor which converts the liquid level into the displacement, and then potentiometer is another sensor which converts the displacement into the voltage level. So this is how this float system works. And then this voltage can be calibrated in terms of the height head of the liquid in the tank. So in this case, you can see what is the issue. This is a very simple method which is used widespreadly at the domestic level, especially. Although it is not considered as a good method, what is the limitation of this method? इसमें कमी क्या है? Although it is used, it is good, लेकिन इसकी कुछ लिमिटेशन है. मेजर लिमिटेशन क्या है? Actually, you will not get the same output for all the liquids. Means if you change the liquid, your output will change for same level, because your float will get submerged by different levels because of the density of the liquid. So as the density of the liquid will change, means this method is not liquid independent. As the liquid changes, your output will change for same level because of the density. Because as the density changes, your float will get submerged at different levels. So it will have, means suppose you have calibrated this output in terms of the liquid level for water. So if you are measuring some other liquid like alcohol, in this case your output will have certain error, offset error, because of the different, either it will your float will get submerged more than water or less than water. So in both the cases there will be some offset. Means offset error means when your liquid in case of when the tank is full and your liquid level is suppose 5 volt, then if you are putting the alcohol, your liquid level, when tank is full, your liquid level, your output may not be 5 volt, it may be 5.5 volt, or it may be 4.5 volt, whatever may be the case. So it is not, so we generally want that the system should be liquid independent, so this is the limitation of it. That's what I had written here. The any change in the apparent mass density of the liquid affects the accuracy. Means you have to recalibrate it. Otherwise, if you are using the older calibration, then it will not be won't work. Means you will have error in your reading. So this is about your float method. Now I want you try to imagine. I want that you should imagine that how can we measure liquid level using capacitive sensor. Again, I had explained what is the meaning of liquid level. Liquid level in a tank. Now you know the capacitance and you know the liquid level in a tank. Now you try to imagine how can we measure liquid level using capacitive sensors. Capacitive sensor is very simple. Um, Capacitive sensor is very simple. Here you see, means if we am talking about the parallel plate capacitor, so if any parameter, your if any parameter, because C will be equal to, is equal to material epsilon whatever you are using. Just इधर जल्दी है. So in this case, if any of these parameter on which capacitance depends, if it changes, then your capacitance will change, and this parameter will change in response to the parameter you're measuring. Like in chemical sensors, your when your sensor is exposed to the chemical, certain chemical, like pollutants like carbon monoxide in the environment, if so its property changes. The insulation material, the dielectric material used, its property changes, so accordingly your capacitance changes. So by measuring the capacitance we can find out the concentration of the contaminant, means pollutant. Similarly, suppose we want to measure the displacement, then we can that displacement will apply this, and then one of the plate is varying or it is laterally varying, then obviously your overlapping area will vary. So this is how your capacitive sensor works. With this background, I'm asking, how will you imagine, how can you, means how this capacitive sensor be used for the measurement of um, liquid level? I want a response from your side. You try to imagine, you try to find out, you try to apply yourself. By the time I'm taking your attendance, you respond your roll call. Roll number 1.
Present, sir.
Roll number 2. Roll number 3. 4.
Present, sir. Roll number 4.
5.
Present, sir.
6.